come from. The thing you may not realize, it comes from atoms, but really specifically Mr. Dimitrievich?
Electrons.
Electrons in the atom.
Getting excited and falling.
So you're carrying some different spheres in your hand.
So we're going to go to imagination land, and these right here, these represent different amounts of energy, and because we're clever this way, we're going to go from the smallest to largest. The golf ball being the least amount of energy, up to the tennis ball, which everyone knows. I mean, we could have gotten a soccer ball or something else, but that would have required way too much planning on our part, so we're just going to go with this. And so what happens is right now, if you can notice here, he's at the first energy level. Lowest energy level possible, we call that the ground state.
So remember, there are 7 different energy levels in an atom.
Right. Are you happy in the ground state?
Yeah, I'm pretty.
Yeah, you're chilling. Yeah, to use a word from our decade. So I'm going to do this. I'm going to never do this. I'm going to never ever break dance again. Let's make that a rule. Here we go. I'm going to toss you one of these balls that has a little amount of energy. You probably missed that because that was so fast.
So when the energy hit me, this is a piece of energy, actually a packet of energy. What happens is it excites me, and then I lose it.
So every time you gain energy, you're going to jump up to a higher energy.
But I don't like being at the higher level. So,
and you're going to release it, and that energy comes in the form of light.
So what just left, the atom, was the light.
Let's try one that's, I figure this is slightly bigger. So let's try a little more energy. This time, it's going to correspond to him jumping from the first to the third energy level.
But I don't like being here. I want to return to the ground state. So
and you'll fall back down.
And now a different color of light was emitted from the atom. So it was one color from level 2 to level 1, and a different from level 3 to level 1.
Let's try a little bit more. Let's get crazier. Let's have you jump up to the 5th energy level. We're going to have a little more energy given to you here.
Wow! It hit me. Okay, I'm not going to jump up because I'll probably hurt myself. But now it is. I'm actually really don't like this.
So we call this the excited state, and no one likes to be in the excited state. We say, I mean, do you want to be JoJo the excited clown boy?
No!
No one wants to be JoJo the excited clown boy. That's not very pleasant. So what do you want to do with that amount of energy?
Release that and fall back down.
Fall back down.
To the bottom level.
To the ground state, we call that. Now,
Yeah.
let's try the highest amount of energy.
Yeah.
I want you to head up there.
Oh, I can't.
So
I gotta be knocked up. So
yes.
Knocked up. There you go. Hit me.
Yeah. Well, just ignore that last part there. Don't get knocked up. So if I give you this amount of energy, now he has the energy that's required to go up to the highest energy level.
I'm at the highest energy level.
Now, really quickly, and this is important while we have him up at the highest level, he ultimately wants to go down to the lowest energy level, the first energy level. But he doesn't have to do it all in one step. It's kind of like the pay-as-you-go problem.
I could lose, but it won't be this amount of energy.
Yeah, it'll be a different
this amount of energy. I'd have like a red ball, and I would jump down to the 5th level.
Right.
And it would release a red ball towards him.
Now, he skipped the 6th, but couldn't he have jumped, theoretically, couldn't he go from the 7th to the 6th?
Yeah.
Or 7th to the 5th, 7 to 4, 7 to... So each time you release energy, it's going to be a different amount of energy.
Right.
Now, what's kind of important, why don't you get rid of all the energy, come back down here. One of the things that's really important about energy is that you can only gain and lose energy in specific amounts. We call that quantization. What that means is that he can be at one energy level or the next, but never in between.
I can't hover here.
So that's what I'm gonna say. Do me a favor, just for all the people that are in the audience, show your skill here. Would you do me a favor, between the 2nd and the 3rd stair, can you just hover between those two? That's way to destroy our example here.
I can't really. That's the problem. And this is the weird thing: is the electron appears on the 2nd level, and even as I fall from the 2nd level to the 1st level, there is no moment in time where I am halfway between there. And they say it doesn't make any sense. And it has to do with the nature of quantization of electrons.
We call that, we're going to learn about quantum theory, so if you ever want to impress your parents, just tell them you're learning quantum theory in school. But here, let's do a good and bad here, right?
Okay.
So, low energy, good or bad?
I like low energy.
Yeah, so we say the ground state, 2 thumbs up, right?
Right.
High energy, any energy other than the first energy level, we call that the what? The
Excited state.
Are you happy there?
Not really.
You're JoJo the excited clown boy. You don't like that very much, so what's your goal ultimately going to be?
Go down.
Now, what you have not noticed here, and even though he's been really fast on this, is how quickly this happens in an actual atom. Can you show me here, just you in real time, moving up one stair? So if he was an actual electron, he could do that 100 million times in 1 second. I feel like you didn't do it 100 million times. Or in fact, another way of
I
saying
did
it,
like 1 in 1 second.
yeah. In other words, he could get up there in 100 millionth of a second. You could jump up and jump back down. I think he did 3 of the 100 million that he could have been doing.
In a second.
In a second. So you need to understand that whenever we see light coming from something, that's due to electrons getting excited and falling back down. And what that
100
means,
million times a second.
so that means that essentially, if you see flickering light, if it goes 100 million times a second, when you see kind of constant light,
It's just constant. So let's talk a little bit more about this idea of quantum mechanics, or this quantum ideas. So to do that, we need this image here. So this represents the 7 layers, electron layers of the atom, the 7 Bohr layers. And what happens is you add energy to the atom. It takes one of the electrons in the ground state. So we've got an electron, and if it gets hit with some energy, notice that Mr. Dimitrievich is drawing it as a curvy thing because it comes in as a wave. It's usually light. What happens to that?
the electrons jump up to
It jumps up to a higher level.
to whatever energy matches the energy that it receives.
So let's say that jumps up to level 3. You're on level 1. And it falls back down. And when it falls back down, what happens?
It has to give off that same amount of energy that it had originally.
All right. Let's say we hit that electron now with a different color of light.
It might be worth noting here that all different colors have different energy amounts. And in fact, if you've ever heard that expression of what are the colors of the rainbow, what is the expression we use?
Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet.
And that goes from the lowest energy to the highest. So red light is the lowest energy that exists, and we have violet that's the
Violet at
highest.
the top. So green would be kind of in between because blue is at the end, right?
So let's say we had that same electron, and I probably should be doing a different color. Let's do a black here, right?
Electron's black, sure.
Electron black. So this is my electron. Now the green, when it comes in, it probably is going to hit it with a little more energy,
Yeah.
right? So I'm going to do that same wave, and it's going to be kind of a little more wavy. And now the electron's going to jump up to, let's say, maybe the 5th energy level.
Yep. And then it's not going to like going to the 5th energy level, so it's going to fall back down to the ground state.
And when it does that, it's going to give off the same.
And then lastly, the blue, we don't have a purple one, but you get the idea. Blue one's going to be the most energetic energy that you add to the atom. It's going to shoot the electron up to, let's say, level 7. And then when it falls back down to level 1, it gives off blue light.
By the way, I'm doing this not so great, but the waves
Will be closer together.
closer together, and I'm terrible at drawing them. And then when you leave, it has to, whenever you're dropping down, you have to lose this amount of energy that matches up. So when you're at the 7th energy level, remember we talked about in the video, you don't have to fall all the way back down to the 1st, right? So if I fell from the 7th to the 6th, the color light would not be blue anymore because that energy drop would be less.
And so it might be a little red light or something
Yeah.
like that.
Now the other thing to be aware of here is this, and I didn't do it as well as I could have, but you see how the energy levels, I meant to do this, are a little bit closer, lower down, and the farther up you go, the wider the energy gaps are. So if you fell from the 2nd energy level to the 1st energy level, that's a different amount of energy than falling from the 6th
to
or
the
the
6th.
7 to the 6th or 6 to the 5th.
Yeah, so the stairs was a bad analogy because each stair was the same height.
Yeah.
But in the electron world, or the atomic world, the levels are not equivalent.
And even crazier is if you go from one atom to another, let's say you go from hydrogen to helium,
It's not the same.
the gap from the 1st energy level to the 2nd energy level for hydrogen is different than from helium.
And it makes sense because remember, there's different numbers of protons, and protons are attracted to electrons because positive attracted to negatives. So having a different number of protons, because what's actually pulling it back down, if you think about it, is the attraction to the nucleus.
Yeah.
The negative wants to be closest to the positive as possible.
So if you have more protons, you're going to have different amounts of pulling on the electrons, and you have different energy levels.
And I want to reiterate this weirdness, right? We say we've got an electron, down here in level 1, right? And then sometimes it jumps up to level 3 right here. But as it moves up here, it's never in between. It magically appears here and then re-magically appears at the ground state. That's quantization, and it doesn't make sense. And it has to do with the wave nature of light, which we'll talk about later.
Hey, so we've been talking about how light is produced, but we probably want to know a little bit about white light and how that impacts everything around us. Yeah?
Atoms have electrons. Electrons fall, it produces light. But when you see white light, what you're actually seeing is all the colors of the light. Remember, we just talked about Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. But when the light hits the white board, what happens?
All of the wavelengths of light get reflected. So as we see this prism right here, when white light enters in, it actually is made up of all the different colors we see, and it's kind of a gradual spectrum. So every single color of light we see comes from the sun. we kind of recreated in the room here with the
our
white
fluorescent
lights.
light. So the white light that's coming from the fluorescent lights you can't see hits the white board, and then it comes to the camera into your eyeballs. And actually, when you see all the colors, Roy G. Biv, your brain says white.
And we get it.
But
Now,
what about if I have a different color? So I have my red face mask.
I'm gonna hold this blue.
So you've got red or blue, yeah. Your blue shirt, the blue face mask. What's happening, what's hitting that? Let's think about this moment. We're in a room with white light. The white light hits the blue thermos.
And everything gets absorbed except this particular wavelength, and it rebounds, and our eye, our little receptors, which we call our eyes, picks it up.
So our eyes see this as blue, but what's only being reflected is blue light. So there's Roy G. Biv hits the light, and only B comes out, right?
Now, and here's it's interesting, because you look at this and we'll say, what color is this? Blue. But it really isn't. If we were to take this next door in here, and I'm sure that would be a great activity for us to do, in a pitch black room, and I would say, what color is this? It's not blue. It's not radiating blueness. In fact, I've heard this said before. In the absence of light, there is no color.
Well, in fact, that leads us to another color. So let's say I have a black face mask. What's happening here? The opposite of black is white. So when the white light hits the black face mask,
Everything gets absorbed.
so there's
Nothing
actually
gets
no
reflected.
reflection. You're not getting any reflection from pure black. Last thing, Mr. Demetrius, I got my red face mask. So when I put my red face mask on, tell me what's happening.
So right now, everything except those red, and I can see some little star colors there as well. One of the things I'm going to time out on this is just to say this. You realize that all of our colors are just reflectors, right? So that reflector right now, he just put on, we don't say, what reflector shirt are you going to wear today? Like you didn't pick a gray reflector that your wife chose out, she chose mine. That's a reflector for just red. All the colors of light gets absorbed in, except for that color that gets bounced back. And again, if you want to get really technical, remember the staircase stuff that we were doing where electrons are getting excited and falling back down? That's what's happening inside that fabric. And so it's kind of a cool thing that it all kind of meshes together.
Up and down, 100 million times a second.
Yeah,
We'll see you guys in class.
look forward to it.